everyone, welcome back to our open class. I'm Desire, and today we're gonna be talking about ROS2 subscribers. So what we're gonna do in this open class is we're going to try and understand how ROS2 subscribers work and how do you get data from, let's say, a topic of a LaserScan topic, for example, or maybe any other topic, right? Because as you know, in ROS2 we use topics as a pipeline for communication between subscribers and publishers. So today we're mostly going to be focusing on trying to understand how to get LaserScan data from one of our fastboats so that we can maybe do something with it later, or we can try to give the robot the ability to navigate or move around obstacles later in other classes. So I'm going to switch to my PC so that we can get to see what we'll be doing and also see how many people have joined us, and you can also say hi. Just hang on one sec. Let me try get us to open the ROSJECT. Alright, so this is what you're gonna see when your ROSJECT is loaded. So I'd like to know is if you all managed to load your ROSJECT or to fork it and then run it. So let me just see if I can see any messages in the chats. Just give me one sec. Okay, there we go. Right, okay, I see hi from Sonia and Alvaro. Okay, anyone else who has joined us, just say hi. Would like to know if you're there. All right. Okay. Can you let me know if the audio is good? Can you hear me? Is the image good? Can you at least see what I'm doing? Can you see what the simulation looks like once it is loaded? Let me know if you may be struggling to have it loaded, or what's your situation. All right. Okay, Sonia says yes, so I'm assuming it is loaded. Okay. Oh, you can hear me. That's good. Anyone else who is still struggling to get the fork the ROSJECT? Alright, so let me just switch to the ROSJECT for now. I'm going to have the IDE open so that we can see what we'll be doing throughout the class. But for now, let's open the notebook a bit more and we can talk a bit more about what it's going to show us, or what we're gonna try and achieve in this class. Okay, so this is what the simulation must look like once it is loaded, and then you can just click on it so that you can zoom and allow your view to give you this perspective where you can see fastboat 1, fastboat 2, and fastboat 3. Right, we will be mostly focusing on fastboat 1. Let me just check the chart to see if there is anyone who might be struggling. Okay. Hey Sarah, okay. Welcome. Alright, so let's see. Did you manage to have the simulation load for you, Sarah, if I'm pronouncing it right? Okay, just let me know in the chat, or if it's still loading. Stream is lagging a bit. Okay, let me just check. Yeah, I think it's fluctuating quite often. But yeah, we'll try to get it to stabilize, I think. Let's see if it stabilizes soon enough. Alright, so let me keep giving a brief description about what we're going to be doing. Alright, so as I've said, if you click on the simulation and you zoom in either using the mouse, you should be able to see the robots loaded like this. And as I've said, we will be mostly using fastbot 1, so everything that we'll do in this one will be in relation to fastbot. And by the way, this whole simulation that we use is part of the packages that we offer and for educational purposes, right? So this is the board box, so it comes with all these panels and this floor and the 3 robots like this, and you can use this for educational purposes, or maybe if you want to practice a couple of things. And mostly this is what it will look like in real life. So the simulation is based off this board box warehouse lab, and you can see the 3 robots, slightly less accurate, but yes, and these are the pieces that you will get in the board box itself. Alright, so as I've said, we will be trying to get fastbot 1 to we are going to try and develop a subscriber that subscribes to LaserScan topics that are being published by fastbot 1, this red one, right? And we're gonna go through the process of creating the package itself. So these are the steps we'll do. So we'll create a LiDAR subscriber package, and inside that we'll create a LiDAR receiver.cpp, right, which is where we'll create our node that is responsible for subscribing to the fastbot 1 /scan topic, right? So let me just check if there is other people. All right. Okay, so as I've said, so we're going to create a node that subscribes to this topic, fastbot 1 scan, right? And after that, we will create a launch file that allows us to launch the subscriber node, or to run that node, so that it starts receiving LaserScan topics that are LaserScan messages that are being published on the fastbot 1 scan topic, right? And then after that, as we do in C++, you will need to link your executables, or you need to compile and then link the executables. That means the files that will run your node, or your binaries that will make sure your node can run correctly after you have created it in the LiDAR receiver.cpp, right? All right, so let me just do let's just do a brief demo in the simulation to just show how best you can see it or move around the robot. So I'm gonna zoom in, and then you can use your mouse, and then once you click on the robot that you want to move, you can use arrows to move it forward and backwards, rotate. So once we have created our subscriber, we will move the robot, right, to various parts of the warehouse, so that we can see the LaserScan readings change, increase or decrease, depending on how far the laser scanner is determining the the things directly in front of it. But for the details of the processing, we'll leave that for another class. Right now, we just want to get a laser scan readings, so that we know that, okay, there is something on this direction of the robot, or there is something in the proximity of the robot, basically. Okay, so You can also do the same for fastboard 2. You can move it backwards by clicking on it. Oops, just one sec. Okay, you can click on it and then move it if it will allow me to do that. Okay, let me just escape this, try again. Still moving fastboard 1. I think there's some screen capture going on, but okay, no worries. For our purposes, this one will be okay. So I'll zoom out a bit so that we can see what we're doing, and let's minimize this and we can go back to this view, right? Okay, so let me just check any messages in the chat. Okay, no messages yet. If you have any questions, feel free to just type them in the chat and ask as we go. Otherwise, I will have to ask questions too, right? If no one asks the question. Okay, so let me just go back here. Okay, so this is where we are, right? So let me just give a rundown of I think let's first create the package. It'll be easier. So we're gonna be doing this exercise, right? So what we'll do is we'll want to navigate into our ROS2/SRC folder. All packages that we create in ROS2 must be created in the SRC folder that is contained within our workspace, right? And our workspace by convention is ROS2 workspace. This one here, you can see it in the IDE. If you want, you can also use the terminal to just if you say ls, right, you can be able to see, okay, which folders do you have in the root directory or your user directory, right? This is the lowest you can go, right? And the ROS2 workspace, this one here, is the one that we're going to get into. And in the terminal, you can do so by doing cd and then pressing ROS or RO and then pressing tab, and then it will allow you to it will autocomplete for you. Then here, if you go ls, you can see there is an SRC folder. Build and install and log, they normally come after you have built something. So for you, for example, you may have an empty SRC folder, or an empty ROS2 workspace, or you may have it with something in it. That's probably because the simulation was built, or it's got some files that it's using from there. So this is the normal structure. You have a build directory, install directory, a log directory, and then the SRC folder. So in the SRC, that's where you put all your packages. So if I go cd and I open this one here and we list what's in here, right, we see there is fastboard description and fastboard RV. So don't worry about this. These are to do with the simulation that we are using, this simulation here. So for us, we want to create our LiDAR subscriber in this directory here, right? So you could do that in the IDE, for example. Let me just check for questions. All right, no questions yet. So you could do that in the IDE by just opening the folders that you want to create your package in. So as I've said, we'll create it in the SRC directory. So here you right click and then you can create a folder. I myself prefer to use the terminal. I think it is also good practice for us to start learning to get comfortable with the Linux terminal as people on the journey of becoming a ROS developer, right? So I'll leave this. So as I've said, you will have to create your package in this directory. So the command that we'll use is this one here. So you can copy this command by just clicking on this icon here, and then you'd maybe Control V or right click paste, right? Control V should be okay, right? So let's look at what we are doing. So we are calling ROS2 package create. That's the command, right? And then here, this is the name of the package we want to create. Then this build type here, so it's a flag, or yeah, let's call it a flag for now. But it specifies the type of package you're going to be creating. So as our class is focused on creating a subscriber for LiDAR data, but that is creating that node using C++, we have to choose the amend CMake package, right? I mean the amend CMake build type. If you are going to be doing it in Python, you will have to use amend Python, for example. Then you have to specify the dependencies, right? So the, let's say, the packages or the libraries that your your LiDAR subscriber package will use, right? So we have this first dependency, right, which is RCO CPP. So this allows us to import the C++ ROS2 client so that we can write our nodes in C++. Right? For Python, you'd have to set your first dependency as RCO RCO Py, right? So that you can use the Python client for ROS2. And this one here, sensor messages, right? Who can tell me what it is going to be used for, or give a direction for why we have to include this sensor underscore MSGS? Let's check if there will be any answers here. Sound check, can you still hear me? Or is the stream stabilized a bit? Alright, let's see. I think we're still having the bit of a lag, so yeah, it's better, but it could be better. Okay, just a bit of latency. Okay, thanks, Sonia. All right, so let's continue. I don't see any questions. If they do come, I'll probably see them a bit later, but I'll do my best to come back to them. Okay, so we were here, right? So I was asking the question, why do we have to include sensor messages or sensor underscore MSGS, right? I will leave that for after we've created the package if an answer is not shown up in the chat yet, but okay, let's press enter here so we can get our package created, right? So now if you do ls in the SRC folder, you should be able to see that you've got LiDAR subscriber underscore pkg, right, underscore package, right? If you look here as well, you can see that it has also been created here. So let's make this a bit wider. Right, so this is our LiDAR subscriber package, and you also see that there is an include folder and an SRC folder created by default when the package is created, and you also have got a CMakeLists, right, and a package.xml, right? So I'm going to give just a brief description about what these files are responsible for. So the CMakeList, this is what is basically responsible for building, and if you know C++, you have to compile packages, you have to compile files and then link them together. All that is done here. You have to specify which dependencies are linked to which executable. So we'll see as we go down into step 5 and 6. Then the package XML, this is basically like where your dependencies are kept. So if you remember what I said earlier, that you need to include the sensor messages as a dependency, here it's already added as a dependency, right? So, and RSC or CPP is also added as a dependency. So remember adding this, or if this is new to you, right, sometimes you may have a lot of dependencies, so you can also add them after you have called ROS2 package create. So if you remember, this command that we have typed here. So we have to specify ROS-CPP as a dependency and sensor messages as a dependency, right? And they have appeared here as dependencies, right? You can see depend, ROS-CPP, and then the closing tag. So if maybe you're dealing with a lot of dependencies, or maybe you realize that you want to use another package later on, right, you can also add them manually here in this file. So it is a good thing to know. If you know all of them, yeah, then you are good by just using by adding them all in the creation command, right? So that's good stuff to know. Okay, so this is the things we have in our LiDAR package. So I'm going to get into it here. So as I've said, I like using the terminal. Sometimes it clears your mind when you get lost in the files structure and everything. So if we say cd and we open this one here, you can also see the files that I was talking about. So CMakeLists, your include directory, your package.xml, and your SRC, right? So in the SRC folder here, this is where we are going to add our LiDAR subscriber .cpp. All right, if that's the correct name, yeah, but I'll check that one, right? So the only thing that I haven't spoken about is this one here. So the include folder, this is where if you're developing maybe very big files, or you want to split implementation and declarations, as you know, in traditional C++ programming, if you have had some previous experience with C++, right, the include folder is where you would have what are called headers, right? So headers are like declarations of your of your classes, if mostly classes, right? So of your classes with their member variables, with their member functions, right? So only declaration, right? Implementation files will be put in here. So if you're familiar with C++, you will know that header files would either have like a .h or a .hpp or a .cpp or a .xx, right? So yeah, so you will basically have header files in this include folder, but for the LiDAR subscriber, there will be a subfolder in it that has got the same name as the name of the package, right? So they will be in here. So again, let me use the terminal for making it clear. So if we say type ls command to list everything in our directory, and then we say cd include, right, we want to open this one here, right? And as I've said, you will have a similar, exactly the same name, but just in the include directory. In this one here, this is where you would have your headers, for example, if you're going to use any headers. Okay, so now with that out of the way, let's go to a section. Let's go further and create our subscriber, right? Because we want to focus on that, right? We want to focus on what code do you need to write to subscribe to this particular topic, right? So let's create our LiDAR receiver.cpp in the SRC folder, as I've said. So if you're comfortable with the IDE, you can just do a right click here and create here. So you'd say new file. So I myself would do it this way, right? So we go here and we get into our SRC folder, right? Then we touch, right? This is the command to create a file. So we say LiDAR receiver underscore receiver, right? It has to match exactly, right, so that we don't run into issues, right? So we have our LiDAR receiver.cpp being created in the SRC folder. Okay, and you press enter. So if you say ls, now you have LiDAR receiver file in there, right? Let's check if there are any questions here. Okay, all good. So we have created our LiDAR receiver.cpp. Now, because we wanna copy and paste this code, right? Let's open the file in the IDE, right? And so this is the file that we're gonna add our LiDAR subscriber, LiDAR receiver code, right? So you could use this but I highly recommend that either use Control A and then Control C, or just highlight and copy, because sometimes if you're using Python and you use this shortcut, you may have spaces that are added, and because Python is sensitive to spaces and indentations, you have issues. So it has become the norm for us to just highlight, Control C, and then Control V in the file that you want to add that code. So let's make this big. So I will just run through this so that we at least get to understand what is being done here, right? Because this is the core of the class, right? So if we look here, we've got our class that we call LiDAR receiver, right? It inherits from RCO CPP node. So it inherits from this node class here, right? And I think if you know that we had to include RSA or CPP as a dependency, right? Here is part of showing why you need that, because you have to inherit all the node implementations or meta implementations, right? Because they are generics that are created so that making nodes would be easier for any ROS developer, right? And then here we have our subscriber, right? So here you can see this is a member variable, right? And it has something being assigned to it. But what I want to do is, let's go and look where it is being declared, right? So here, this is a member variable subscriber. It's given the name subscriber underscore, right? And it is of type pointer, right? This is all that you need to know right now. But what I want you to at least get from this is that it has to be declared somewhere before being assigned something in the constructor, like is being done here, right? And then the same thing applies to the timer, right? It's declared somewhere because it's a member variable. If you've used Python before, this is where you declare your variables that you're going to use in your class, right? This is the same thing that's happening. It's just that in C++ you have it done like towards the end of the class, right? The same thing here. You have your last scan as another member variable, right? And it's of type shared pointer, right? So in C++, the last thing here that you have is the name of the member variable. This one is a type because C++ is a type strong, right? You have to have a type to declare a variable. So if you're going to have integers, for example, you have to specify what type. You have to say int, then give that integer a name. The same thing applies here. We have a size t type and we call it min.index, right? Min underscore index. That's the same thing that's happening here. So going back to our constructor, right? So when the LiDAR receiver is created, right, we give it a name, LiDAR receiver, right? This is how the node is known. So when you do like in a listing of nodes when your code is running or in your ROS2 environment, this is how the node will be called, right? It will be called LiDAR underscore receiver, this name in brackets here. And then what we are doing is, to our subscriber, right, we are initializing it with this here. So we are creating a subscription to the topic fastbot scan, right? But what is happening here in the angle brackets is that this is what is called a template argument. So we are not going to go into much detail about that, but what we are simply trying to say here is that we are trying to tell our compiler to say create a subscriber that uses this particular message or that communicates via this message and subscribes to this topic, because this topic uses this as an interface, right? So it uses an interface, or it uses a message type that is called sensor underscore MSG LaserScan, right? So we'll check in the terminal to see what does this type of message entail, right? And then after that we have this 10 here. So just to give a brief description of what it is, so this 10 here, it's the amount of messages that your subscriber will keep, right? So anything that goes beyond, let's say it's now gets 12 or 11, for example, the last two or the oldest two will be deleted, let's say, right? So it will keep 10 most recent messages, right, in case the processing is not happening at the same speed that the information is coming, right? So, and then we have this last section here. So this is all happening in the creation of a subscriber, right? Because you see there's the blue parenthesis here, and then there's the blue parenthesis here, right? So this last one here, what we are doing here is that when we create our subscriber, right, that we call LiDAR receiver, right, we are saying every time you receive a message of type LaserScan here, right, every time you receive that message, call this function, for example, right? That's what is being what's happening here. Call this function that we call scan callback. So the function will do the processing, right? So every time a message comes of LaserScan, right, it triggers this scan callback to do some type of processing, right? So this is what you would have to deal with maybe when you want your robot to use LiDAR scan data for maybe avoiding obstacles or going around a track, or maybe just figuring out what is in front of the robot, for example, right? And this stud bind here, what it does is it binds this function here, right? It binds this function to the instance that we have created. So remember, you can create multiple LiDAR receiver objects, but each instance is its own callback, right? So that you don't have a crossing over of callbacks, right? You don't have a crossing over of the functions that are being called regularly by when LiDAR scan data is received, right? So that's enough of that. But let's just look at what's happening here. We have what is called a timer, right? So this timer basically determines how often the processing is done, for example, right? In this case, because I've said every time data comes in or from our LaserScan topic that is called fastbot here, fastbot_1 right, we have to process that at a particular rate. The timer is responsible for telling the node that, oh, I know you're receiving it a lot faster, but I want you to process it at this time, right? And then here we're just logging our information to tell us in the terminal or during execution to say, oh, the node is started, right? So this is the function that I was saying is being bound, right? And it does some processing. We are not gonna get into the detail of what the processing is, but the idea is this function is the one that is called at a particular frequency, right, to get the processing of LaserScan data. That's what's important for us to know right now, right? And again, this is the callback that I was saying will be responsible for giving us or determining the pace at which something is happening within our node, right? We can have various times, right, at which this stuff happens, but that is solely dependent on what this time is going to be, right? So you can have 500 milliseconds, you can have 1,000. That just means that there will be a longer time before you get like this message being printed out, right? So you can see here there is no calling of this function here, right? So this again from my explanation should at least give you an idea that, okay, if this in the timer, if we are not calling this a callback here, that just means that this callback is just going to process things as they come, right? And this one will just be responsible for giving us information only, because you can see all that is happening is logging or specifying, okay, if you have processed the last LaserScan data, then tell us that there's no more data to process, right? So is this clear? Is this understandable? I want to see if there are any questions, so let me just check here. All right, no questions so far. Okay, let's go back to get a bit more detail or to make this code run, right? Because we want to see it work. So I will resume here to our normal Outlook, and then let's continue. So this was step 2, right? We've added the code to the LiDAR receiver .cpp, right? So this is the code we've added. Now, in order for us to run this, we can run it in 2 ways. So we could use what are called launch files, which is what we're gonna do here, right? So in ROS2, launch files are basically Python files, but that take on the responsibility of running the nodes that we would have created, right? The other way is maybe you could use ROS2 run, but you'd have to specify, okay, the package and then the executable. When you specify ROS2 launch, for example, you also have to specify the package and the executable. I'll do a breakdown of that when we launch our node. But for now, just copy this code, and we're gonna put it in our LiDAR receiver.launch.py. So where do launch files go? Okay, that's another question. So I'm gonna do it here in the terminal so that we at least have a clear understanding of where we are, right? I could try and tell you here, but for the sake of simplicity, I think this one is a simpler way of doing it. Okay, so if you go and you list the contents of your LiDAR subscriber package, right? So this is where we are. I've just cleared, right? You can just type in clear like I've done, right? If you've got too much, to just clear your terminal. So like this, clear, you press enter, and then it will be cleared. You're only left with where you are. So I'll list again, and we've got include, package.xml, src, and CMakeLists. Here, this is where you create if you're using launch files, you would have to create a directory to put your launch file. So if you say mkd, so it's basically a shortcut for make directory, right? And then you type launch. So you're creating a directory that you call launch. So by convention, all the directories that contain launch files for ROS2, they are put in this directory. So your directory has to be launch. If you share your package with someone else, they won't struggle to try and find out where do they find the launch files, right? Because they will be in a very specific, known, convention approved file, right? So then we're gonna enter this directory here. So we're gonna go into our launch directory, and then again, if you remember what I've said earlier, you use the touch command if you want to create a particular file. So it can be any other file, a Python file, a launch file, a CPP file, a TXT file. Just use touch. So I'm gonna call it here LiDAR receiver, like we have it labeled in our notebook here, right? So LiDAR receiver dot launch dot py. So this is how our launch files are named in ROS2, and then you press enter. List, ls is shortcut for list, so you can see that our file now appears in there. So once it appears, you can go here to open that file so that you can add contents to it, right? So if you just go here and you double click, and then you should be able to see, okay, you've got an empty file that is called LiDAR receiver .launch.py. Right, if you wanted to do it in the terminal, it will be a bit complex, and it will take some getting used to, but it's possible. If you go if you call vim, for example, right, and you say LiDAR, right, it opens. So you'd have to learn the specifics of vim to be able to do that, right? But I wanted to just show you that it's possible to do that. So let's add our code to that launch file. Hang on, let's just do Control A, Control C. Okay, all right, and then we save our launch file, right? Let me just check if there are any questions. Okay, no questions, all good. All right, so let's continue. All right, so now the fourth part, right? So we have added the contents of a launch file. So let's just talk a bit about what the launch file is doing, right? So we are importing, like, launch description, the various dependencies that we would have to use to launch our ROS2 package. What's important is, so this structure is very much the same for all the nodes that you probably create. You will have maybe more import statements, depending on what you're doing before your nodes launch. But I think what is important for us to speak about here is this stuff here. So we have a package that we call LiDAR subscriber underscore package. It's the very same name, right? Because we want to launch our executable that is contained in this LiDAR subscriber package. So this is our package here, and the name must match here because the thing that we want to launch is contained in that package, right? And then there's an executable here. So this one will speak a bit more about it. If you remember correctly, we have not seen a name that is good, that is written like this, or this is the first time we're seeing this name, right? But again, it's an executable, right? And the output just means that everything is output to the screen, right? So let's do things to clarify why we have this that we call executable here, right? So the next step after you've created the launch file is, as per our notebook, is you will have to make sure, or let's say you'd have to create a platform for compilation, or you have to link your executables, or you would have to compile your code first, and during the process of compiling there is also what is called a linking phase. So if you remember, in ROS2 we have to compile our packages, right? Whether it is a Python package or a C++ package. But what you have to understand about C++ as a language in general is you also have to be aware of how your packages are linked, right? And part of the process of linking packages comes down to this file that I spoke about earlier. So this is the CMakeList file. So it is responsible for making sure that you have the executables linked to the right dependencies. So if you remember, when we created our package, we said we wanted to have RC or CPP and sensor messages as dependencies, right? So those are dependencies that we have to be linked to our executable that we that it will be responsible for running this node that we have created here in this CPP file, right? So let's add this into our CMake list, and then I will go through them bit by bit. Let's just Control A, Control C, and then let's have this in full view, and we'll open our CMake list here. So in the CMake list file, you have this already existing things. I'll just highlight them like this. These things, they are created for you by default, and they are important. So what you will do is you just press enter twice, and then you can paste the code here, right? So remember, you have to put it before this line here. So you have to put it between end if and a main package. If you put it after a main package, your package won't compile. So anywhere above, I think, should be fine. But this is generally what we do, right? We put it here. So let's talk a bit more what is happening here, right? So in these three things that we've added, so there are three, you could call them declarations or function calls, but in CMake language they're probably not that exactly, but for the sake of simplicity, let's just call them declarations or function calls, right? So there is this install, right? This is the first one, and then there is this installation, that's the second one, and then there is this one here, amend target dependency is the third one, and then there is this one, which is the fourth one. So these are the four things that we have added to this file, right? But we want to understand what each one of them is doing. So this one says add executable. So we are saying, after, when the compiler works, when the ROS2, the CMake compiler is working, we want it to create an executable that is called LiDAR subscriber underscore node. Right, now this is the second time this name is shown up, right? So remember, I said that this name here appeared for the first time here, right? You can see it's the executable, right? So this executable that is being called by this launch file when it runs is actually being created when the compilation process happens. And when the compilation process happens, it happens following what is specified in the CMakeList file, right? So if you look here, we have the name, right? So our executable is going to be called LiDAR underscore subscriber underscore node, and then we have to specify where the source file is found, right? So the source file is found in the SRC directory in a file that is called LiDAR_receiver.cpp. So this is our source file. So what we are basically saying is to the compiler, you have to create an executable that is called LiDAR_subscriber_node, and you have to find the source code in src/LiDAR_receiver.cpp, right? This is where you will find the source code, right? And what we are doing here is amend target dependencies. We are saying after you create that executable, you have to link it to these other libraries, so to say, right? These are the dependencies. So what is going on here is that LiDAR subscriber executable, right? This LiDAR subscriber node cannot do without knowing or without being linked by this, because it uses the contents of RC or CPP and sensor messages, right? And then what we're doing here in this third directive, so to say, right, is we are just installing the executable in the library, right? In the library you find in let's see, it should be in the install folder, right? So you can find, so from previous compilation you can find that there's also this lib here. So that's what you are doing here. You are installing it there. So what the launch file will do is you to go look for that executable there when it launches your node, right? And then here you are installing your launch file. So here you install your executable, right? The things that will be called by your launch file, and here you install your launch file, so that when you run ROS2 launch and you specify the package name, so ROS2 launch LiDAR subscriber underscore package, and specify the launch file name, the launch file can be found. So again, specify this is the launch file name, it can be found. If you do not do the installation here, if you do not install, right, ROS2 launch will not find your launch files, right? Because this will be missing. So it's very important to have it there. Okay, so let's just check for questions one more time. There are not any yet. Okay. All right, so let's go back to our discussion. Okay, so let's open the notebook to see what the next step is going to be. So after this, so we've added our dependencies, we have added the specific lines that we need in the CMake list. We've also added code to our launch file, and we have also added our source code to our LiDAR.receiver.cpp, right? So the next thing is you'd have to compile the package, right? So to compile the package, every time you must switch to your ROS2 workspace root directory. So the workspace is this one, right? So you have to go back there before calling callcon build, right? So you can do that by specifying the path. So you can do another cd again. So cd double dot just means go back one directory backwards, right? So in this folder, this is where you always call callcon build. So unless you are working with workspaces that are overlapping each other, ideally always call callcon in this workspace, right? Your default workspace. The rest is left for more complicated stuff, depending on how much overlap you wanna do in your building of ROS2 packages. So I think that's good enough explanation for now. Just remember that you always have to call callcon in your workspace. In our convention, or in the ROS2 convention, it's normally in the ROS2 workspace. You may have other workspaces. For example, if you remember, here you have a notebook workspace, you have another workspace that is called web page workspace. They've got nothing to do with us, but I'm just saying that workspaces can be labeled differently, but you must know what the root directory for your workspace is. But in ROS2, if you name it correctly, it'll be easier for anyone who's working with your package to know what it is. In this case, it's ROS2 underscore workspace. So this is where you must call callcon build. So let's copy this command, and then I will specify try to give a brief explanation. I think most of it is self-explanatory. So we are calling Cocon build, right? So we are using Cocon to compile and build our package, right? And then here we say packages select a LiDAR subscriber. So this is mostly used when you have so many packages and you don't want to build all of them at once. If you just call Cocon build and you do not specify which package you want to build by using package select and then specifying the name of the package, Cocon will recompile everything. So if you have very big packages, that can be very time consuming. So you want to specify the package you're going to build. So in our case, we are going to specify that we want to build our LiDAR subscriber package, right? So let's press enter, see if it builds, and give it some time. All right, so as it builds, let me just check if we have any messages. No, none. Okay. Okay, 50%. Okay, so our package is finished compiling. So what you have to do next is, before you call either ROS2 launch or ROS2 run, you have to source the install directory. So what the source command does is it tells your terminal, like this terminal here, that every time you want to call like ROS2 launch or ROS2 run, it also searches the current install folders for your workspace, for example, right? So if you do not call source, right, anything that was built in this compilation cannot be found because you have not sourced it, you have not allowed it to be discovered in the available executables, so to say, right? So what you're going to do is we're going to source that first, and the way you do that is by using source install. So the source command is doing exactly as I've said, and then install is actually where those executables should be found, right? So, or not where there's executables exactly, but where to find any of the declarations you use in the in you calling something like ROS2 launch or something like ROS2 run. So we're gonna say source install setup base, right? And then now we can actually call ROS2 launch LiDAR subscriber, right? This is the command that will run our launch file here so that it starts running, right? So I would have wanted to do an example where you try to run it without sourcing. I don't know if it will work here. So let me try to do this. If this terminal had not been sourced automatically, so let's go open that, and then okay, so it just sourced it automatically. But yeah, you get what I'm trying to say. So the idea is, if you don't source, sometimes your recent the effects of your recent compilation will not show because they won't be sourced, right? So let's go back here, and I think we can stop this one. Yeah, so right. So let's run our LiDAR subscriber node, right? So this is the node that we're saying is responsible for receiving data from the LaserScan data that's being published by the Fastport 1, which is this red one here, if you remember what I said. So if you run our LiDAR subscriber, as you said, okay, it says no scan data received, right? So it says no scan data received, maybe because there is some data that's stale or something. But first of all, let's do ROS2 topic list, because we want to see, okay, is the topic there and is the data being published, right? So we want to see, okay, why is it that it's saying it's not receiving any data, right? So if you let's clear this terminal for a little bit and then do ROS2 topic list, right? So we want to see, is the fastboard a fastboard underscore one scan available, and if it's available, is the data being received, right, or is the data coming through via that topic, right? So if you go ROS2 topic list, right, it will list all the topics that are available, that are currently running, right? So you have got here the fastboard one scan. So this is the topic that we have subscribed to in our subscriber node right here. That's why we had to specify fastboard underscore one scan, right? So the next thing that we'll do is we'll try to echo this topic, right? So it's ROS2. So echoing is like, it's like a process of seeing what is being received in that topic, or what is being passed through that topic, right? So if you say ROS2 topic echo, and then we specify our topic, the topic that we want to see data coming from, right? So fastboard one scan, right? And you can press tab once you type SC, right? And then the terminal will autocomplete for you. So right now, it seems like there is no data coming. So let's wait for it to see if there's anything that will show. But it's probably something with the simulation, or let's try to move our robot towards the wall or towards some other place. So right, so it's here now. It's too close to the wall, and let's see if we have anything coming here. So still nothing. I think we might have to restart the simulation if it doesn't show this the topic. So the other way you could, if it doesn't show the messages, the other way you could try to see what's going on is if you go ROS2 topic info, right? You should be able to see the amount of subscribers and publishers on that topic, right? So fastboard one scan, right? And now here you have one publisher. Yeah, clearly our robot is publishing data, but it's not, we don't see that the data is coming, right? And this is the one publisher, right? So because fastboard one is the only robot that is publishing on the fastboard scan topic, on the fastboard one scan topic. The rest, the green one and the blue one, they are publishing on different topics. They are publishing on their own topics. If you look at the topics here, we have got fastboard underscore two scan, and then we have got a fastboard underscore three scan. So fastboard three, the blue one, also published on that topic itself, right? So that's good. We know that our publisher is there. Let's just try one more time to echo that and see if anything comes. All right, let me just check messages just for now as we wait for it to load. Okay, no messages yet. All right, let's try restart the simulation if it will allow me. But okay, restart. Okay, it's loading very slowly, but anyway, we'll see. Let's talk a bit more about some of the stuff. So this is the command that I was saying you could echo if you want to see what values are coming via that topic, right? Or what information is coming via that topic, right? So let's do some form of introspection, right? So we want to know, how do you find out information about a particular topic, right? How do you find out information about, for example, the scan topic? How do you know the type of message that you would have to use, for example, or that you'd have to specify when you create your subscriber? For example, if you remember what I said here, so you have to know, right, what this is going to be, right? You have to know what message type is does your topic publish, right? So one way you could do that is you could do that via ROS2 interface show, right? So we'll say ROS2 hang on, interface show, and then you say you have to specify the topic, fastboard 1 /scan. Hang on one sec. Interface show, fastboard 1 scan. Hang on, let's do this. So you could say, if you type in like ROS2 interface show and then you press H, you can be able to get like information about, okay, what other things do you need to add to that command to get the information you want, right? So what the stroke H means is just means help, right? So you can get more information about the type of message or the type of argument that you want to pass. So if you saw here, so type show in interface definition, e.g. example interface is msg string. So in this case we know that it uses this, right? And if you look here, if you look at what we did earlier, so where's that? If I can find it quickly. I think I probably have cleared it. Okay, no worries. But in this case, it's telling us that we need to say interface show of the actual message type. So if we go ROS2 interface show, and then you're using sensor messages, you get that via the topic info actually. So if you say topic info, right, ROS2 topic info, and then you specify the topic, so fastboard 1, and then you say scan, right? Now it tells you this is the type of message type that it works with, right? So when you run ROS2 interface show, you actually want to see what is this interface or what is this message type comprised of, what data values does it expect one person to receive or to at least make use of when they do a subscription to that, right? So what we should have run earlier is we should have run ROS2 interface show and then specified the message type. So you'd say sensor messages msg / LaserScan, right? And if you press tab, it doesn't show up because there are multiple. So now you can see that this is what the sensor, the LaserScan message looks like. So it has got various values. So it has got angle mean, so the smallest angle, right? And then angle max, the greatest angle. So basically this is the sweep of the LiDAR scan, right? So how much data does your LiDAR sweep, or how much let's say the total distance or the total angular distance that it covers when your LiDAR spins, right? So that's the angle max that you get here, so the end of the scan. So if your LiDAR scan data gives you like 20 values in a 360 degree rotation, right, your angle max would be like 360 if it spins that much a distance, right? And then you also have like angular increment. So angle increment is basically the resolution. So if your LiDAR is spinning, right, but it's spinning and giving laser pulses like every like 20 degrees, so your resolution would be like an increment of 20 degrees, right? You have to convert that to radians because this one works with radians. So that basically determines what amount of angle is left in between the previous scan and the coming scan, right? So if you have a LiDAR scan that pulses a lot more frequently, then you have a smaller resolution, your angle increment will be a lot smaller. Then the time increment, basically, if you look here, it says if your scan is moving, this will be used in interpolating position of 3D points. But basically, this time increment determines the time between different pulses, right? So if your LiDAR is rotating and you have got let's say 2 seconds between each pulse, right? So time increment basically can be able to allow you to determine, okay, what is the distance between this thing and that thing, for example, if you're using it for 3D, for example, right? And then we have range mean and range max. So range mean is where your LiDAR should consider the things to be too close to the robot, and then range max, obviously you cannot set it to infinity, because if you do, then everything else is considered to be an obstacle, right? So you have to limit range max as the furthest distance that your robot can look to, right? And then you have the ranges, which is basically like the data that you have to process when you receive here. So ranges data is basically all the scan values that you get, or that you actually will be working with when you use the subscriber, right? And then you have intensity. So these ones are basically, it's normally an empty array, so it doesn't have any values. But if you are working with reflective surfaces, where like you have maybe dull surfaces and very shiny surfaces, intensity values, the intensity array is reserved for holding or keeping a recording of the energy with which the received pulse is received, right? So when a pulse is sent, right, to the surfaces that we've got, right, and it bounces back, basically intensity's field is responsible for keeping a record of how much energy did that pulse return with, right? So that's basically what your LiDAR scan, your laser scan interface is like, right? You can look at more of these definitions in this section of the notebook here, right? So angle mean, it gives definition, angle max, angle increment, and then range mean, range max, time increment, the scan time. So basically the scan time is the total time to do a complete scan, right? So if you imagine that your laser sensor is spinning, right, to do a complete scan it has to spin to come back to the original position. That's the time, right? Then you have angle mean, angle max, angle increment, range mean, and range max. So I highly recommend you go through this so that you can understand more in detail what the interface is like, or what the laser scan interface entails, right? So if I could get this to load quick enough, maybe I'll be able to show you like the amount of how your laser scan indexes change when the robot goes forward or backwards, right, depending on the proximity of the obstacle. So in this code that we have developed here, you have this logging section that's responsible for telling you, okay, what is the furthest obstacle, right? So this basically looks at all your ranges data and then tells you, okay, the ranges data that has got the smallest value without actually including the very minimum, right? If you look at this here statement, it says if ranges I, so a particular entity of a ranges data is less than minimum range and the range itself is greater than the minimum range, then it's considered to be valid. Once it's underneath the minimum range, if you remember what I said from our definition, then it's not considered, because then you have to give your LiDAR scan a sensor, or the way you process LiDAR scan data, you have to give it a circumference to start from. Otherwise, even the robot's body will be considered to be an obstacle itself. So you have to give a certain radius, or let's say a diameter, away from the robot, where you say this is range mean, right? So if you look at the first board and you know the dimensions of the first board that we're working with, right? So let's say let me just use an image. I think that'll be easier as we wait for the simulation to load. So if you look at here, we have our first board 1, right? Okay, it is loaded. We'll go check now. So if you look at first board 1 here, so range mean will be the distance around the robot, but not including any parts of the robot, right? Because you don't want the robot to consider part of its extension to be an obstacle. That's what it's there for. It's there to protect your LiDAR scan data from detecting things that are part of the robot itself. Okay, so I think the simulation is loaded, so let me just try to run ROS2 topic echo scan to see if we can receive our data. Topic echo first board. Okay, first board 1 scan. Okay, and now we are receiving data values. Okay, so that's good. So what we want to do now is we want to run our LiDAR subscriber, right, so that we can move the robot around to see how it changes or to see if it will receive the data, right? So we can call ROS2 launch, and then you specify that you want LiDAR. You have to specify the package first, and then you specify the name of the executable, right? So if you remember, our executable was LiDAR subscriber underscore node, right? So if you press tab, it must work if I'm correct. Hang on. Okay, no worries. It's probably not able to find it, but let's try. Okay, because I typed it wrong. Okay, let's go and see and just get the whole launch command. So it's called LiDAR receiver. We wanted to launch the launch file. Okay, no worries. So let's launch it using launch, and then so the one that I was using where you have to know the executable name, that's when you're using ROS2 run, not ROS2 launch. But now you can see that it's receiving values, right? And it's even telling us that the closest obstacle is like at 0.3 meters away from the robot, right? What I want us to do is let's make this a lot bigger, and we can move it around to see how does this value change, right? This closest obstacle, right? As we move the robot backwards and forth. And then you can tap here. You can use two fingers to zoom in, or if you've got a scroll ball, you can use that as well. So we're gonna click on it, right? Give me 1 sec. Okay, so if you click on the robot and you use the arrows, right, you can see now the distance is reduced to 0.1, right? You can see because we're very close to the wall. If you rotate the robot like this, it's still 0.1. Let's rotate it in other direction. Now you can see it's telling us that the furthest obstacle, the closest obstacle actually, is 0.26. So my assumption is it's this wall here. You can see that, right? So if we move until the point of collision, right? So now our robot is collided, and you can see here. So hang on 1 sec. Let me leave this. Okay, so if you see here, so it doesn't read 0, right? Although our robot is already collided with the wall. So that is basically because of the fact that our LiDAR scan sensor, this gray thing that sits on top of the robot here, is positioned in the center of the robot. So there is a bit of distance between it and this wall, this panel here, right? So if you remember from what I said about a range, the mean range, right? Imagine if you had made in mean range to not account for this part of the robot that extends beyond your sensor, right? The robot might consider itself to be an obstacle in some cases, but this is 2D LiDAR, so you can just consider it to be planar, so it may not run into issues. But in cases where your LiDAR scan sensor sits like in between poles, for example, or these yellow pillars, let's assume, you will have issues because they will be considered to be like obstacles, right? That's why you always want to specify the ranges mean, or that's why the interface has got that option, right, for specification. Okay, I'm glad this worked. Let me just look for questions if there are any. All right, I don't see any questions, so yeah, that was basically our LiDAR scan data subscriber, right? So basically it's the process of receiving data from a LiDAR scan sensor and then doing something with it, right? So we could use it to allow our robot to navigate, or to allow our robot to be able to detect things so that it doesn't crash into them, although we made it crash here by choice, right? Okay, so yeah, I hope you've learned something, and you can basically take ROS2 basics in 5 days in with C++ to be able to get into more depth about this kind of topics. And also, if C++ is still quite new to you, I highly recommend the course that we have here at the top. So this is ROS2, I mean C++ for robotics. So this is a free course. You can do it without needing a subscription. So if you still need your C++ language to be polished for the sake of usage in ROS2, that will be a very good start. We'll basically be focusing on the C++ that we use when we develop ROS2 nodes or things for robotics using ROS2. Alright, and then, yep, that's it from my end. And don't forget, you can acquire this for yourself, or if you're an organization and want to teach others, this is a very good foundation to start having the ability to write code and see it execute on the actual robot, right? And then you'd have the wonderful transition from simulation to the real robot, and then understand the nuances. So our boardbox package does that very well. It's a very good learning material, a very good learning platform as well. So yep, I wish you a very good week from now on, and I look forward to seeing you on the coming Tuesdays. So let me switch to my screen here, and maybe let me just check for messages first before we wrap it up here. So okay, let's see. All right, no more messages. Okay, all good. So thank you, Sonia, thank you. All right, so let's go to our section here, and then we can get back to seeing me. All right, so yep, that was that, and I hope you got something from it, and I'll see you next week. Bye bye.